Hello and welcome to week 7 of Basic Business Statistics. This week we're going to be talking about relationships between variables, something we call correlation. Now this section, correlation, is something that is covered in a rather scattershot or disjointed way in our textbook. And that's why I want to take a deep dive on it this week to unite a lot of these ideas. So in our text, we've learned about things like scatter plots when we talked about graphing. And today we'll be talking about variance and covariance. And then later on, there's another chapter that goes into correlation. But all of these ideas need to be united, brought together in your mind, because correlation, correlational research, is foundational to so much of what we do in statistics. Particularly when we get to applied statistics and we start looking into things like regression modeling. To understand all of that, you need to have a background in correlation. And the good news is that correlation is easy to understand, much more so than the hypothesis testing examples that we'll ultimately get to. This is very straightforward. It's about relationships between variables. And specifically, the relationships that we'll be looking at today are variance, covariance, and correlation. What do I mean about relationships between variables? For this example, let's imagine that we are running a concession stand for a football game. And the two variables that we are interested in are temperature and the amount of certain products that we sell at our concession stand. So let's examine what happens when the temperature goes up. What happens to the sales of cold soda? When it's hot outside, we're going to sell a lot more of that icy cold soda. And of course, when the temperatures drop, then we'll sell a lot less of that cold soda. Those two variables move together. We can predict that we will sell more soda when the temperature is hot, less soda when the temperature is cold. As the temperature goes up, what happens to our sales of hot chocolate? In this case, warm temperatures outside mean we're not going to sell very much hot chocolate. But when the temperature starts dropping, the sales of hot chocolate are going to increase. These variables move opposite of each other. A third example, as the temperature goes up, what happens to the sales of those foam #1 fingers that we sell at the concession stand? Here, there's no relationship between temperature and sales. And so we should not see a change in the sales of these foam fingers based upon temperature. There's no relationship between these variables. Correlation, you can see in the name, is about relationships, specifically relationships between variables. Correlation measures the extent to which two variables are related. And what I mean by related is that changes in one variable are consistently associated with changes in another variable. As I teach you about correlation, I want to first back up and remind you about a few techniques that we've already learned, specifically the mean, the standard deviation, and z-scores. Let me start with the mean. Remember, the mean was where we took all of the scores in a data set, added them up, divided by n, and that gave us an average. And then we were looking for the average deviation. And to compute an average deviation, we took all of the scores in our data set, subtracted the mean from each score, and then, actually before we added them up, we squared them, because if we just add them up, they will add up to 0. Squared each of those deviation scores, added them up, and then divided by n. And that gave us a measure of variance. So variance is the degree to which a variable deviates from its mean. But what if we have two variables? Each variable has its own variance. However, those two variables, if there is a relationship between them, might vary together to a certain amount. And this is called covariance, the degree to which two variables deviate from their respective means. Now also let me remind you of z-scores, or standardization. If we standardize the covariance We essentially create what amounts to a z-score by dividing by the standard deviations. We create a correlation coefficient, which is the standardized covariance. It's the covariance divided by the variance of x times the variance of y, leaving us with a measure of how much those two variables move together, either positively, moving up and down together, or negatively, moving one goes up and the other one goes down. Correlation is the standardized covariance, and that correlational coefficient is something that we're going to spend a lot of time with. Also, let me remind you of the scatter plot. Here we have a scatter plot of height and weight. There's lots of little dots on this scatter plot, and there's a line that moves through the middle of those dots. That line is called a regression line. It functions a little bit like a mean. The scatter plot graphically displays the strength and the direction of the correlation, and is depicted with all of these dots, which are called data points. Each data point is a combination of an x and y value. In this example with height and weight, we would measure your height and your weight. We'd plot your height on the x-axis, your weight on the y-axis, and create a dot that represents the intersection of those two numbers. This would give us, when combined with everyone else in the class, a series of dots on our x and y axis. Each dot is a pair of x and y scores. So the sample size for this is the number of pairs. N equals the number of pairs. And then mathematically, we would draw a line among all of those dots, which best represented the line of best fit is the line with the least amount of error in predicting all of these dots together, which is called a regression line. It visually represents the relationship between the variables. So with that as our background, we're ready to talk about the correlation coefficient. The correlational coefficient, which we'll write as R sub xy, was created originally by Sir Francis Galton, who, like Wile E. Coyote, was a genius. But the idea of correlation was perfected by Karl Pearson, and we will call that correlation Pearson's R, which essentially measures how close all of those data points fit to a straight line. This is what a correlational coefficient looks like. R is the abbreviation for this. R does not stand for relationship, it stands for regression. And you'll also notice that it is in italics. R, equal sign, the sign of the correlation, the positive or the negative, indicates the direction of the linear relationship. If it is positive, or if there is no sign, there is a positive relationship between the variables. In this case, the negative sign indicates there is a negative relationship between the variables. The absolute value of the number, or the decimal, indicates the strength of the relationship, with numbers closer to 1 indicating a stronger relationship, and numbers closer to 0 indicating a weaker relationship. So let's drill down a little bit on this positive, negative, and the strength of the relationship. What can we learn about correlation? A positive relationship, or a direct relationship, occurs when both variables move in the same direction. As we saw with our example at the concession stand, as temperature goes up, sales of cold soda go up. As temperature goes down, sales of cold soda go down. That is a positive or direct relationship. Another example would be height and weight. As you grow taller, you tend to weigh more. We put one variable on the x-axis, the other on the y-axis. We use the variable on the x-axis as our predictor variable. And I'll tell you more about prediction as we move along. The other direction that can occur with a correlation is a negative or an inverse relationship. This is where the variables move in opposite directions. As temperature goes up, the sales of hot chocolate go down, and as temperature goes down, as it gets colder, sales of hot chocolate increase. Another example might be that the more that you study, the fewer silly mistakes that you make. We would put our predictor variable, the amount of study, on the x-axis, and we would use that to predict the number of mistakes, which will be plotted on the y-axis. The strength of the correlation is the extent to which any given x value, any predictor value, is paired with one and only one y value. If there is a perfect correlation between variables, all of the dots will fall on that straight line. Every dot will be on the regression line. But for most correlational coefficients, they are not a positive or negative 1. They're somewhere between 0 and 1. Correlations at 0 mean that there is no relationship. But the closer those values get to either positive 1 or negative 1, the stronger the relationship between the variables. A strong correlation has an R value close to either positive 1 or negative 1. There is a consistent relationship between these two variables, and all of the points converge on a straight line. When the relationship grows weaker, those dots move off of the line, or they are further from the line. As our correlation is approaching 0, we have a greater inconsistency in the relationship between the variables. And when there is no trend among these data points, then R collapses to 0, and there is no relationship between the variables. The scatter plot becomes circular or elliptical, cloud-shaped. There is no relationship that is evident just by looking at those dots. We can also apply the concept of variability with our correlations. As variability increases, the differences in the y-scores at each x become larger. You can look at how closely the dots fall on that line to make a determination of the strength of the relationship or the amount of variability. High variability means a weak relationship. Low variability means a strong relationship between the variables. We need a way of interpreting our correlations. Now, one very simple way to do this is to simply look at the correlation coefficient itself. When we have correlations from 0 to 0.24, we would say these are weak correlations. From 2.5 to 4.9 are moderate correlations, and anything 0.5 and above would be a large or a strong or very strong relationship between these variables. Now, this is just a good rule of thumb that we can look at and we can make some determinations. But we also need a mathematical way of determining the strength of these relationships. And to do that, we square the correlation coefficient. And this creates an effect size for the correlation. The squared correlation is called a coefficient of determination. This is the proportion of variance in one variable that is explained by variance in the other variable. Remember, we're trying to use our correlations ultimately for prediction. We will use our x variable to predict our y variable. So how much variability in the y variable is predicted by the x variable? Or to use a real-world example from a real dissertation, the effect size for burnout, which was an R squared of 0.42, indicated that a large portion of the variability in job satisfaction, 42%, was accounted for by the level of burnout that the counselor experienced. Notice that the R squared of 0.42 can be easily converted into a percentage just by moving that decimal and adding a percent sign. A 0.42 is 42%. When we create a coefficient of determination, there must be something left over, because you remember these values have to add up to 1. If we subtract our coefficient of determination from 1, we get the coefficient of alienation. It is the proportion of variance in y that is unexplained by the x variable. And returning to that previous example, 58% of the variability in job satisfaction was explained by factors other than the level of burnout among counselors, such as low pay, excessive paperwork, and inadequate health insurance. By squaring the correlation coefficient, we can now measure the amount of predictive ability of x on y, the Coefficient of alienation tells us what is left unpredicted. And now we have a setup where we can add another variable to a regression model that might also help us to predict y. So now maybe we have 2 or 3 variables that ultimately predict y, and the interaction of those 3 variables together leads us to something called multiple regression. This next concept is something that I've heard repeated from people who claim to know very little about statistics. It's all about the relationship between correlation and causation, and it's often described this way: correlation does not equal causation. In this comic, we see a little boy complaining, "I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy." Now, you can't blame him at all for coming up with this inference. He sees the sign come on, and then he feels the bumps. That's how causation works. One thing happens, and another thing invariably follows. However, this is a correlation. It is not the seatbelt sign causing the turbulence, but rather the anticipation of the turbulence that the pilot notices causes the pilot to turn on the seatbelt sign. Let's explore this interaction between correlation and causation. First of all, correlation does not imply causation. If there is a correlation, even a strong correlation between variables, that does not imply that there is a cause and effect relationship between those variables. However, causation implies correlation. If there is a causal relationship between 2 variables, there will be a strong correlation. If the cue ball strikes the 8 ball and causes it to move, that causal relationship will result in a strong correlation between cue balls striking other billiard balls and causing movement. And we can infer from that that if there is not a correlation between variables, then there is not a causal relationship either. I've previously referred to a research project that I participated in which we measured the effectiveness of abstinence-based sex education on decreasing the rates of teen pregnancy. Another research project discovered that the states that have the highest rates of abstinence education also have the highest rates of teen pregnancy. Now, people who supported this approach to education said, but that's correlational. Correlation does not imply causation. And that is absolutely correct. Correlation does not imply causation. But if abstinence education did in fact cause teen pregnancy to decrease, we would see a strong correlation between them. We would not see abstinence education being associated with higher rates of teen pregnancy. What happens with correlation is that although it doesn't imply causation, correlation can suggest causation. You see, the presence of a correlation does not preclude causation. And if someone tries to dismiss unwanted correlational data by saying correlation does not imply causation, while that is technically true, correlation will sometimes stand in the corner and say, look over there, and point to something that is causational. What we as researchers then do is follow up on our correlational data using different methodologies, research methods, to try to tease out where the correlation, or where the causation really lies. When there is a correlation between variables, it says nothing about the direction of causality. So for example, rates of exercise correlate with rates of obesity. It could be that when you don't exercise, that leads to increases in obesity. But it could just as easily be that increases in obesity make it more difficult to exercise. We haven't established a direction of which is predicting which. Or, as the number of bars in a community increases, there is an increase in the number of churches. So there's a positive correlation between bars and churches. Does that mean that with all of those sinners, we need lots of churches? Or does that mean that all those religious people can really drive you to drink? Well, neither one. What explains the positive relationship between correlation and causation? It is the amount of population in a community. With more people, you have both more bars and more churches. There is a third variable that is explaining the relationship between these two variables. Well, now I want to talk a little bit about how we do correlational studies and how those contrast with an experimental design. In an experimental design, the researcher manipulates an X variable to see what happens in a Y variable. If we're doing a drug study, we might manipulate whether or not a certain cohort receives the drug or a placebo. We control that part, and then we're measuring an outcome in their health. But with correlational designs, we do no manipulation. We simply observe variables as they occur. Many times, this is because there are certain studies that cannot be done ethically using an experimental design. For example, let's say that we want to study the neurological effects of caffeine. We want to know, does caffeine cause jitters? Is this something that we could do where we give one group of people caffeinated coffee, a second group of people decaffeinated coffee, and then we measure them on some performance measure? Absolutely. This is an experimental research design. Now we want to know something about the relationship between smoking and cancer. Does smoking cause cancer? Could we randomly select a group of individuals and make them smoke a pack of cigarettes a day, and another group not, and then measure their rates of lung cancer later on? Totally unethical. We cannot do that. But what we could do is measure people who are already smokers against those who are not smokers to look for those rates of lung cancer. That is a correlational design. Correlational designs will allow us to do types of research that we could not do ethically using an experimental design. How then can we calculate covariance, correlation, and create a scatter plot using Excel? For this example, we will be using the Dog Toys 2 Week 7 dataset. Open up that dataset in Excel and go to the second tab, which is labeled Correlation. You will see that there are 3 columns, the dog number, the random identification number, and the 2 scale variables that we have in this dataset, days to failure and toys owned. We're going to use days to failure to predict number of toys owned. Our theory is that if you're the kind of dog that chews up your toys, you won't have as many toys. Let's see if there's a relationship between these variables. We will create the variance for days to fail by placing our cursor in cell F3 and then typing $var.s, open parentheses, and our data range is B2, B51. To create the variance for toys owned, we'll do essentially the same thing. $var.s, and this time our data range is C2 to C51. Now we create the covariance of these 2 variables together. Type $covariance.s. In parentheses, our data range is B2 to B51 for our first variable, comma, C2 to C51 for the second variable. And we've created our covariance. To create the correlational coefficient, we will use the formula CORREL. And again, the data ranges are B2 to B51 and C2 to C51. To create our coefficient of determination, or our effect size, we will square the correlation coefficient. There's no specific formula for this, just type F6 caret 2 in order to square it. Now you will remember that we had an outlier in the number of toys owned, that value of 20. We're going to fix that outlier And then we're going to recalculate these values to find out what happens when we remove the outlier. And that also tells us the effect that an outlier can have on our values. Before we fix the outlier, we're going to begin by saving the values that we have already created. So select the range of cells from F3 to F7 and copy. Now place your cursor in I3, the first of the gray boxes, and choose Paste Special Values. This copies over only the values, not the formulas. This can be our reference data. Now we're going to fix the outlier that exists in the toys owned data. Now the outlier was a value of 20. So we find that value, and we're going to Windsorize this value to change it to the next highest reasonable value. Well, the next value below the 20 is a 14, so we're going to change this 20 to a 15. Excel automatically recalculates all of our variances and covariances, and now we can see some comparisons. So originally, our variance 1 was 17.57. That didn't change because that variable didn't have the outlier. But for toys owned, the variance dropped from a 14.03 to an 11.69. Less variability, more consistency. The covariance strengthened. These variables now have a stronger relationship without the outlier. And the correlation also improved from a 0.24 to a 0.31. The effect size increased as well. Removing the outlier decreased the variability and increased the strength of the relationship between our variables. So our next step will be to create a scatter plot. We'll select our data first. Just select columns B and C. We don't need to select the specific range of the data. And then click on Insert. And under the recommended charts, we can find the XY scatter option. And from there, we'll choose Scatter. This creates our basic scatter plot. Now, I'm going to use a few of the tools here to make this a little easier to format. Let me start with the quick layout. And I'm going to choose Layout 1. I'm also going to save myself a step by changing the colors to a monochromatic gray. That changes the colors of all of the dots. Let me do a little bit of cleanup. Let's start with the x-axis. We'll click on the x-axis, and then we'll explore the axis options. Now we know that the minimum was a 1 and the maximum was a 20. So let's leave our minimum at 0, but set the maximum to 20. We're going to do the same thing on the y-axis. So click on the y-axis. Our minimum will stay at 0, but the maximum will also be 20. And the major units, let's keep that consistent with what we have on the x-axis. Let's change the major units to 5. I'm going to delete the horizontal lines by simply clicking on one of them and delete. And I'm also going to resize this scatter plot a little bit. I can change the axis titles for the x-axis. This was the days to failure. And on the y-axis, I can change that axis title to toys owned. For the chart title, I think I'll just delete that for now. And the legend out on the right, I'll get rid of that as well. The last thing to add would be the regression line, which we will get to through Add Chart Element. We'll choose Trend Line Linear. That creates a line. Let me click on that regression line and I'll make a few changes. First of all, I want to change the color of this regression line to black. And I want to make it not a dashed line, but a solid line. All right, that looks pretty good. So we now have a scatter plot and we've created our variances, covariances, and our correlation. And finally, I'm going to show you how you can do your correlation using JASP. I'm going to use the dogtoys2.jasp dataset that I created last week. I double click on that dataset and it opens JASP, and then it opens the dogtoys2 data. All of the analysis that I have done previously is saved within this JASP file, but I'm going to create a new analysis. Under the option for regression, I find correlation. I'll use the classical version. The two scale variables that I'm going to use are days to fail, which I'll move in first because that's my predictor variable, and then toys owned. We see that the sample correlation coefficient by default is Pearson's R. Let's select some additional options. I like to change the table to display pairwise, especially if I'm doing correlation, there's only two values to report. We want to report significance and flag significant correlations, and also let's get the sample size. To get the scatter plot, under plots we see scatter plot. And the regression line this time is added by default. We take a look in the results window. We see that there were 50 pairs of scores. The correlation is a 0.24. The probability is 0.09, which is greater than 0.05. So this is not a statistically significant correlation. And we also see in the scatter plot that there's only a slight upward incline describing the relationship between days to fail from the toys and the number of toys owned. So there is a weak to moderate correlation between these two variables. So perhaps rather than dogs who chew up their toys having fewer toys, maybe their dog parents buy them replacement toys when they chew up the old ones. It's just what we do. Well, thank you for sitting through this video. That's all that we have for this week for correlation and variance relationships between variables.